Today we're going to be talking about gradient and gradient descent. This video is going to be pretty short because I feel like there's not as much to talk about compared to the other videos, so I will try to keep it short because I know some of my previous videos were pretty long. But anyways, getting straight to the point. So yeah, when we talked about the loss and the loss function, I think maybe it was hard to visualize, so I wanted to start off with this website here. Um, it was a it was a project created with Fast AI, and it shows how the loss landscapes of deep learning work and the optimization process. So what we're going to be seeing is we're going to simulate the descent trajectories, and we're going to also see everything take place live. So I think that I talked a little bit about some of the activation functions, and if you remember, ReLU is one of them. And as you can see, this weird shape here, it's definitely not linear, it's very complex, and the reason it's able to be this complex is because of the activation function itself, because ReLU introduces nonlinearity. So I'm not going to go too much into why it does that. I think that's something you guys can look up on your own, but all you need to know is that this activation function helps to make things not a straight line only. So this button that I'm clicking here is going to allow us to have a a ball that we get to roll down this hill, and it's going to show us the optimal way to get down. And here I can adjust the speed. So I think that I'm going to keep it pretty low just so you guys can see it rolling down so you can see what's happening. And just to give context before I actually get to it is the reason we want this ball to get to the bottom is because the bottom means that the error rate is pretty low, ideally pretty much none. So the higher at the top of this mountain looking thing we are, that means that the error is higher because this is representing a cost function. The higher up it is, the more cost there is. So we want it to be low. We want our loss to be very low, and we want to find the global minimum. So I'm gonna start here. Gonna the ball's gonna roll down, and we're gonna see how it reaches the bottom in the most optimal way. Let's check it out. So it's going pretty slow. Let's see if I can zoom in. I think I'm gonna actually I realize this is way too slow. I'm gonna increase the rate. Can I increase the rate? Yeah. Oh, suddenly that went really fast. Yeah, unfortunately that went really fast, so you guys couldn't see it, but yeah, you could see here that it tried to find the most optimal way to get to the minimum. And here's one thing you need to realize is that it didn't get to the absolute minimum. Uh, and let me see if I could show it from a different angle. Okay, here. So we're gonna put it again. It's gonna roll, and look, it didn't go to here where my cursor is because in the eyes of the loss landscape or the gradient descent, it believes it found the most optimal way, even though we know by eyeballing it that isn't the case. But um, a computer and the algorithm itself, I should say, it wouldn't know that. So, anyways, the importance of this whole demonstration, it might seem silly, it might seem like I'm just rolling a ball down a hill, but the main point you want to see here is that this whole landscape is the loss, and we're trying to find the best way to get to the bottom of this um, mountain, you could say, because that would mean that we have very little to no loss there. And look, did you notice that when I made the learning rate too high, it kind of bounced. Let's do that again. Let's go pretty slow, just for reference. So I'm gonna go slow. Look, it smoothly finds the bottom. But when I crank it up to the max, it bounced. It kind of missed some stuff there. And in the end, it kind of worked, I guess. But honestly, like, I could have cranked it up more in a real world setting. I think that this website just has its limits. But that's the catch, because we don't want the learning rate to be too high. Imagine that I crank this up even more. The learning rate would just cause that ball to completely miss that bottom of the mountain. Maybe it would even fly off this whole graph here and go to the void or whatever. So that's that's one really important thing to take note of right there, because in gradient descent, when we're trying to calculate the gradient, we want to make sure our learning rate is appropriate, because if it's too little, the ball goes too slow, like you saw in the beginning. But if it's too big, it might completely just fly to outer space. So, yeah, uh, I guess an analogy I would say is if that if that that learning rate is too big, it's kind of like trying to find the bottom of a bowl with a giant pair of stilts. It's just really inefficient. So I think that's a common misconception a lot of people have. They think, oh, just make the learning rate huge so I can get the optimized result ASAP. Um, so I want to go back to my code now. I I wanted to talk a little bit about the the zeroing. I don't know if you guys remember in my first video, I talked a little bit about backward as well as zero, and I noticed something weird. It's that every time we take a step in the loss, you would think it looks like we're zeroing out what we remember in the gradient, because if you remember, the zero kind of resets what the gradient remembers. And if all of this sounds foreign and you have no idea what I'm talking about, you should probably go back to video one, which talks more about this. And sorry, not video one. I believe it's also a bit of video two, so you might have to watch both videos one and videos two if you don't understand what I'm talking about or if you're new to this episode. Um, so uh, the reason being for this zero is that you got to think of it, you got to shift your thinking to thinking about it kind of like a GPS. Once you've taken a step towards your destination, you need to wipe out the old directions that your GPS had given you and look at the map again to see the new directions for the next step. Because if you keep remembering the step you had already taken in the past, it gets confusing. It doesn't make sense, um, and the AI tries to follow the old downhill directions from where it used to be, not where it currently is, if that makes sense. So that's why it's important to um, reset the directions of the downhill descent in every iteration, because each iteration is a step, right? Um, and specifically, what we're looping through are the epochs here. Each step is being an epoch. And again, I covered this before, but an epoch basically just means a training cycle. Um, so on the site, we see the ball rolling down. Now, in my notebook here, we see that I have a function attached to my tensor called loss.backward. And if you remember, um, that tensors have special properties and features, such as the computational graph. They have a history of everything that was done to them. So to the untrained eye, this loss variable will literally look like a scalar number, but in reality, it's a summation of many operations and maybe some matrices collapsing, whatever. And um, in the end, now we're literally, how should I say this? We're literally calculating the tilt of the mountain. So every time we're calling backward, we're calculating this tilt. We're calculating how steep it is, how to traverse this mountain in the most efficient way possible. So again, going back to my code, when I'm doing where is it? Right here in this line, when I'm doing dot sub parentheses coefs grad times learning rate. So the dot gradient or the dot grad is calculating how steep it is, the mountain, and the learning rate is how fast we're going to traverse that mountain. So again, you can think of it in that line of code that I'm literally pushing the ball down one step at a time down that hill. So that's pretty much gradient descent. It's I feel like it's pretty scary. It sounds scary, but once you know what's going on, that it's literally traversing this cost function, which looks pretty crazy, and trying to find the minimum to optimize the loss so it's as low as possible, it's pretty straightforward. I mean, of course, there's more to it, but that's the overall picture here. And thanks for listening, guys. I hope to see you next video. And next video, we're going to finally be deep diving into code, how I built a neural net from scratch using PyTorch. See you.